The first of these equations, which was equivalent to Gauss's law, as we found, along with the Lorentz force equation, is what is called Gauss's law of electricity. Gauss's law of electricity can be stated in two forms, and we have only discussed the integral form of this. There's also a differential form that we only discuss in a more advanced course because it requires vector calculus. Gauss's law of electricity says if we have a charge, and this charge therefore emits an electric field in every direction, if we take a surface around this charge and look at how much electric field comes out multiplied by the area here, which is an infinitesimal area, d sigma, this is d sigma, and take the product of these two vectors all over any surface, and it doesn't have to be a sphere, then the integral, the sum, the continuous sum of E dot d sigma as a vector, and these are formally vectors right here, is going to be equal to the charge that's inside divided by epsilon naught. Now we've already discussed this equation before, but we need to remind you that this is a closed surface. We draw this circle here to mean closed, and it's a surface, which means we add up everything here. And it does not have to be a sphere. We could have a plus 3 coulombs here, a minus 2 coulombs here, a plus 5 coulombs here, and we could have a minus 7 coulombs over here. We could have a very irregular surface that was like this. And if we integrate over this surface, then this equation, or Gauss's law of electricity, which generalizes the sphere, which we discussed earlier, allows us to say this negative charge over here will have an electric field, but the electric field will come in one side of the surface and go out the other side of the surface, therefore contributes nothing. Whereas the charge that's inside, the electric field goes out in every direction, or in every direction. And so if I take the algebraic sum of all the charges that are inside and ignore the charges that are outside, that will give me this integral. So this would be 5, 6, 7, 8 minus 2, which would be 6 over epsilon naught. And of course you require that our constant k is 1 over 4 pi epsilon naught, and k was equal to 9e to the 9th, to a very good approximation. That allows us to calculate the numerical value of epsilon naught very, very accurately from this equation. So this is our first of Maxwell's equations, and it is useful in actually determining the electric field in cases of a lot of symmetry. We did that for the plane in a previous section. We did it for a capacitor, which is a pair of planes, one positive and one negative, with equal charges per unit area on them. We did it for a line of charge, where we had a lambda charge per unit length, and you can also do it for a cylinder, where we have a cylinder here, and we look at the electric field that comes out from the cylinder. So special configurations, as we have shown, can be, if the geometries are highly symmetric, then we can use this law to determine the electric field very easily, as opposed to trying to do it by integration and adding up all the contributions from the vector from the various individual charges. So again, this is Gauss's law for electricity, and it tells us that we have sources for the electric field. And if we have closed surfaces around those charges, then the total charges that are inside divided by epsilon naught will give us the integral of the electric field through that surface.